Hello, my name is Ziang Yan. I'm a postdoc at German Center for Cosmological Lensing. I'm very happy to be invited in this Cosmology from Home. Today, I'm going to talk about cosmic star forming history from Galaxy-CIB cross correlation. So star formation is a very important topic in cosmology and astrophysics. It has a lot of physics beneath. For example, galaxy formation, matter content of the universe, accretion, and feedback processes. According to some previous studies, we currently know that star formation started at redshift about 6 to 20 and increase until redshift around 2 and then decrease until now because there's no not efficient gas to make stars. And there's some typical method to study star formation activity because we cannot directly see star forms in distant galaxies. So what we do is to measure the flux of galaxies and link their luminosity to stellar population and star formation rate by assuming some luminosity function, initial mass function, and accretion model, and etc. But this method has some potential problem, is that this method is based on to study a subsample of galaxies and measure their flux individually. So that's probably affected by selection bias or incompleteness. So another method that can solve this problem is through an observable called cosmic infrared background, or CIB. So CIB is the cumulative infrared emission from all galaxies throughout cosmic history. So because it's the IR radiation from all galaxies, so there's no there's hardly almost no selection bias. So we can just see all the IR radiation from galaxies. But what generates CIB? So the CIB is mainly generated from thermal dust emission from star-forming galaxies. So in those star-forming galaxies, the stars, especially young stars, emit UV radiation, which are absorbed by interstellar dust and heat the dust up at a temperature of around 30 Kelvin, and then re-emit in infrared. So that is a CIB. And so from studying CIB, we can learn, as I just said, we can learn dust properties at dust temperatures, or star forming history, which is the main topic of this study, and also galaxy distribution, since CIB are mostly from galaxies. And so the model for CIB is here we use the model proposed by Maniyar et al., which links the CIB emissivity with star forming rate density and spectral energy distribution of dust. So here, this J nu is the CIB emissivity that is depend on redshift. So the rho SFR is called star formation rate density, which is defined as stellar mass formed per year per volume. And this SEFF is the spectral energy distribution of dust, which depend on the dust thermodynamic properties, including temperature and other stuff. And this K is a Kennicott constant, which links SFR with the infrared radiation. So in the context of halo model, the star forming rate density is a integral of star forming rate in dark matter halo with halo mass m times this halo mass function and integrate over halo mass. So this SFR in this model is proportional to a lognormal distribution of halo mass. So this m peak is the halo mass where star forming rate is most efficient. So this is one of our model parameters that describe the star forming rate. And what we want to do is to apply CIB observation and constrain this rho SFR in different redshift. And as a summary, the CIB anisotropy model includes such three ingredients: the spectral energy distribution, star forming rate, and star forming galaxy abundance. So this, I did not show it in the previous slide, but that is modeled by the halo occupation distribution, HOD model. So there are two plots here. The first one is the spectrum of mean CIB, which shows the spectral energy distribution. This is a study, this is a result from a previous multi-wavelength study. So this shows the CIB luminosity in different rest frame wavelengths at different redshift. And the right panel is the previous study, the star forming rate history from previous studies. So those points with arrow bars are star forming history probed by multi-wavelength galaxy surveys. And those two lines are fitted from the CIB anisotropy study, the previous study. And you can see clearly this increase and then decrease. And there are some previous CIB anisotropy works, including cross-correlation between CIB and CIB itself, which is the CIB power spectra, and CIB cross CMB lensing, and also CIB cross TSZ, etc. But those studies are all like cross-correlation between two projected maps, which are not very sensitive to the redshift distribution of CIB. So in this study, we propose a new method by cross-correlating CIB with galaxies in a different galaxy sample in different redshift. That is called tomographic cross-correlation, so which is shown in the right plot. So for example, if you have a galaxy sample around redshift 0.5, then you cross-correlate that sample of galaxy with the CIB map. Then what you see is actually the CIB. So what contribute most is the CIB at redshift 0.5. So we can study the star formation rate at that redshift. Another advantage of galaxy position is that they are relatively easy to measure because we only care about the positions. So it's not like lensing or CMB lensing that we have to do some extra work. And the signal to noise is pretty high because the CIB are mainly generated from galaxies. So you would expect a pretty high correlation. And the tomographic cross-correlation can trace the SFR history better. And we can also separate our galaxy sample into different types so that we can study the star formation rate for different types of galaxies. So that is a very interesting study. So the galaxy data we are using in this study is from the kilodegree survey kits. So the kit gold sample has 5 tomographic beams from redshift 0 to about redshift 1.5. So this plot showed the redshift distribution of this 5 tomographic beams of kit galaxy sample. And the dotted line showed the redshift distribution of CIB. So we can see that the redshift coverage of kits is relatively low. It's at the climbing stage of CIB, is not at the peak. So, but future study like LSST, which extend to a deeper in the sky, might reach this peak redshift of CIB. But in this study, we can only probe CIB or star forming history until redshift 1.5 about. And the CIB data we use is from a CIB map made by Lenz et al. So they use the sky map produced by Planck and make 3 CIB maps in 353, 545, and 857 gigahertz. And these two plots show the CIB map in the north and south pole in galactic coordinate. So the transparent band shows the key's footprint. So the overlap range covers about 1% of the sky. So here is our cross correlation measurement. So we have 5 tomographic bins, 3 CIB maps. So in total, we have 15 cross correlations. And we use a tool called Namaster to correct the bin and mode coupling due to the mask. And we measure the cross correlation from L equals to 100 to 2000. We get a pretty high signal to noise, which is 143. So now we have the measurement, and we fit the measurement, the cross correlation measurement with our proposed model. And the left plot shows the posterior. So we have 3 fitting here. The Kian contour is a fit from cross correlation only. And the purple shows a cross correlation and some external star forming rate measurement. And the red one shows the externals, the fit from external star forming rate history. And we see that those 3 measurement gives consistent constraint on our star forming rate parameters. Here we have 4 SFR parameters. Eta max is the maximum efficiency of star forming rate, and M peak is the halo mass where we have maximum star forming rate. Sigma m and tau describe the width of the log normal distribution of star forming rate with respect to halo mass. And we also see that the fitting is actually pretty good. For this cross correlation, we have a chi-squared, reduced chi-square equals to 1.14. So we conclude that our model works fine, and also the fact that they give consistent constraint means that the cross correlation is indeed a valid probe to this star forming rate topic. And from the constraint, we derive the star forming rate. So there are 2 plots here are both star forming rate density, and they differ only in the x-axis. The left panel is lookback time, and right panel is redshift. So from the right panel, we see that constraint is not very good above redshift 1.5, which is expected because our kids galaxy sample only so the redshift is mostly less than 1.5. So any redshift above that is not well constrained. But you comparing with some previous studies, we see the star forming rate is consistent with previous studies, which is a good news. The error bar is relatively big because the sky coverage of kids is pretty small, only 1%. So this can be improved with future studies. I jump to this slide. But anyway, so and also from the constraint, we can study a very interesting interesting parameter, the peak mass, and we make a comparison with previous studies on the same parameter and get a consistent result, which is around 10 to 12 solar mass. That gives you the most efficient star forming rate. So for some future studies, which covers larger part of sky and extend to deeper in redshift, we make a forecast for 2 ongoing and future surveys, including Canada France Imaging Survey and LSST. So CIFIS is a survey covers about 3,500 degree square degree, and redshift range is similar as kids. So if we look at the the green contour here, you can see that the constraining power is almost the same as our cross correlation plus external SFR constraint. And for LSST, which has a much larger sky coverage and deeper redshift range, the constraint is also much better. So that means this will improve this constraint a lot. And so future study with this new surveys on CIB galaxy cross correlation, we will inform us more about cosmic star formation history. So here's a conclusion and some future prospect of our study. First of all, we make a pretty significant detection of CIB galaxy cross correlation, and the Halo model fits well with the cross correlation, and we have a consistent constraint on star formation rate history with previous studies. And we also conclude that the halo mass with most efficient star formation activity is about 10 to 12 solar mass. And this is a pretty potential study in that with future studies, the constraint on SFR will be better. So we can introduce more sophisticated model by introducing like feedback and crunching and other physics into the model to make it more sophisticated, complicated. And we can also, as I just said, we can also prove star formation rate with different types of galaxy, and we can also try to constrain dust SED. So that is all. Thank you for listening.